Welcome back. This is the day the Lord's made. Let us rejoice and be glad in it. In this video, I'm going to talk about intermolecular forces, intramolecular forces, but focusing mostly on intermolecular forces for covalent substances, as well as other related ideas like boiling point and vapor pressure and other things connected to intermolecular forces. So this is for DC chemistry, week 31, our notes in brief. So intermolecular forces versus intramolecular forces. An intermolecular force is a force that's between two different things, between two different molecules. So if you had a water and another water, the force between the waters holding the waters together would be considered an intermolecular forces. These things tend to influence like your physical properties, like what's your boiling point, what's your melting point, how much energy is between the substance to be able to pull it apart, your lattice strength, your lattice energy. So intramolecular forces, the only difference is RA, so intra, this is between atoms in the molecule holding it together. So think of it like intramural sports. This is when people within an organization are participating with each other, not with an interscholastic event. So these things tend to influence the chemical properties. Like, for example, what makes HCl, hydrochloric acid, a strong acid? It's because the intramolecular forces between the chlorine and the hydrogen are weak. Therefore, the hydrogen is willing to leave. All right, so that's enough for now for that, because basically we're going to spend all our time talking about intermolecular forces for the rest of this video, because this is a more important topic as far as our content we want to cover. So different types of covalent intermolecular forces. We should mention that we don't talk about intermolecular forces with salts and metals. That doesn't really exist. All right, so covalent intermolecular forces are all we'll be focusing on here. All right, and I have these organized from weakest to strongest, assuming that mass is the same, because eventually if you get big, it's hard to pull you apart. So the weakest intermolecular force for covalent substances is the London dispersion forces. London dispersion forces are the idea that we might at any given moment have a random distribution of electrons, and they're not situated how they're supposed to be. All right, so consider helium. He has 2 electrons. If both electrons end up being on the left side of the atom temporarily, what happens then is we have a temporary negative charge on the left. So if all electrons are over here, all 2 of his, it ends up having a temporary negative and a temporary positive charge. Again, this is not a permanent thing. However, the fact that the electrons had switched to the left side means that a helium next door would also be influenced by this, because now this helium has a temporary negative charge and temporary positives. So this helium's electrons are going to move too. They're going to move towards that. And so when you think about London dispersion forces, think about this like electron swishing and swaying for everything. So imagine like bazillions of molecules. If one's electrons move to the left, everyone's electrons move to the left, and then everyone moves right. And it just kind of goes back and forth. It's a temporary attraction, but it's enough to hold them together to make it a solid. But again, they're very weak. So again, helium is not going to solidify until it gets really cold, because it's a very temporary small attraction. However, even though this is the weakest force, eventually if you just get big, then this becomes the primary thing. If you're just a ginormous molecule, this is a very large force. So for example, water is a polar molecule, and we talk about, oh man, water has such a high boiling point for his size, but water still has nothing on some very, very large hydrocarbons. If you have like some hydrocarbon with 17 carbons long, it's probably a solid. All right, 17 to 20 carbons long, it's this long molecule, it's gonna have a higher boiling point than water, just because even though it's nonpolar, it has so many electrons to swish and sway to help hold together and hold on. Next step up is dipole-induced dipole. And dipole means, for you guys, polar. If it has a dipole, it's got a positive again. A polar substance and a nonpolar substance results in something that's going to have a dipole-induced dipole, because the polar is going to influence the nonpolar one so that it has a polarity. So if we take some molecule which has a permanent dipole, like water, as a positive and negative side, and it comes near something that's nonpolar, what happens is the nonpolar one's electrons will swish and sway so that they line up. So this thing used to be neutral on the surface, now it has a positive side next to the negative side. So London dispersion, everything in this class will focus will mostly be on if you have nonpolar substances, dipole-induced, polar plus a nonpolar. Now dipole-dipole, this is if you have 2 polar things, and those line up with the positive and negatives attaching. Again, we're getting stronger here. They're holding on better because they have a permanent place to grab, permanent place to hold. So here we have H and Cl hanging out, H and Cl hanging out, 2 hydrochloric acids. this force between H and Cl would be a dipole-dipole interaction, which is relatively strong. So